Okay, this video is for AP Calculus, and we're talking about, uh, we're in the unit on integration, and we're going to talk about something called the definite integral and Riemann sums today. This is a big topic, so we'll cover it in two videos. And at first, this is going to seem like it's completely disconnected from yesterday's topic of antiderivatives, but those two things are connected together, and we'll explore that later when we look at the fundamental theorem of calculus. All right, so to begin, I'm going to define something that we've hopefully been exposed to in the past, something called sigma notation. Whenever we need to add things up, we can use this symbol here, the capital S in the Greek alphabet, which is sigma, to show how to sum things up. Like you can have some rule here, and then if you plug, this is called the index of summation, this I, starting at some number and ending at some number, then you plug C in for this I and whatever the rule is, and you get the first term. Then you add 1 to that, and you plug that into the rule, and you get some number, and you keep going until finally the last thing you plug in is D. And then you sum those things up. So this is a symbol for what we call summation. This is called sigma notation. A couple quick examples. Let's say we have a rule here that says the rule is 2k plus 3, and we are going to sum up all the terms that are generated from this finite series if k starts at 0 and goes up by 1 until we get to 3. That means you would take the rule and plug in a 0, so you'd get 2 times 0 plus 3, which is a 3 for the first term. Then you'd increase this by an integer to 1, and then this becomes 2 times 1 plus 3, which is 5. Then you'd go up to 2, which is 2 times 2 plus 3, which is 7. Then you'd go up to 3, and that's 2 times 3 plus 3 is 9, and then you'd stop. So this index of summation is going from 0 to 3. And then this symbol right here says to sum, S for summation, S for sigma, to sum up these values and get a single number, 24, which is what this rule generates if you sum those four terms together. Here's another one. The rule is I squared, not the imaginary I, just an index. And if I goes from 2 to 5, that's going to be 2 squared plus 3 squared plus 4 squared plus 5 squared, which adds up to 54. Okay, we're going to see this notation used to express certain ideas in this unit. So it's good to just quickly remind ourselves of how it works. Okay, so the main idea here is, let's say we have a function curve, and we have a region in the domain from A to B, x equals A, which is lower, to x equals B, which is higher number. And we want to find the area under the curve, meaning the area between the function curve and the x-axis. We find that area. Okay? Well, one way to do that would be, it's going to be hard to calculate this because there's a curvature shape here. But we could attempt to kind of fill this up with a simpler geometric shape like rectangles, which are easy to find the area of. The area of a rectangle is just the height times the width. And we can sum those things up. So if I did attempt to approximately fill that area up with rectangles, then the area would just be the sum of from rectangle 1 to rectangle n, if I had n rectangles, of those individual rectangle areas. Right? And what happens, how close that is to the real area, depends upon the geometry of the situation. You could say to set the height of the rectangle equal to the height of the function curve, and do that at the left end of each of the intervals. If you did that, you would get rectangles that fill in this manner. That's referred to as a left sum. Or you could use the heights at the right of each of the intervals to determine the heights of the rectangle, which is called a right sum. Or you could use what's called the midpoint rule and take each rectangle's interval and use the x in the middle of that to establish the height of the rectangle. Right? And whether or not these are over or underestimating the area is going to depend upon the specific shape of the curve. Okay, so whichever rule we choose to use, left, right, or middle, there is a chosen x value which we plug into the function to establish the height of the rectangle. Right, so first we might want to figure out how wide these rectangles are. So if we have x from x is a to x is b, then this width of b minus a is dividing by the number of rectangles if we want to make the rectangles equal width. So the width would be b minus a divided by n rectangles. And that's how wide this little width is. This width here would be b minus a divided by n rectangles, that width. And we could label that delta x if we wanted to. It's a change in x. Right. So what would be the value for one of these rectangles? Well, if we chose the left end, which is probably the easiest, we could just say, if I want to take this first rectangle, and we want to do, I guess if we want to do the right end, we could say the first rectangle, just start at A, start at this A, and then just add one width to that. So if I just added a single width, if I started to A, that, and I added this width of B minus A over N, that would give me this particular X value right here. And then we could use that to plug into the function to get the height. Right? If I wanted to, say, find this rectangle and use the right-hand side, we would have to add 1, 2, 3, 4, 5 widths. So we would start with A, and then we would add 5 of those widths that are each B minus A over N to get to this X value here, plug that in to get the height, and then multiply by the width to get that little area. So the height is going to be the function value with that particular X plugged in. And then if we just take that as the height and multiply by this width here, that's going to give me the area of that one rectangle. And then if I want to sum this up to try to find an approximation for the area, I'm just going to sum from rectangle number 1 to rectangle number n those heights times widths. This is a really complicated notation, but it's really for a pretty simple idea. We're just going to pick a different x in each of these rectangles, maybe using the right-hand side, plug that into the function to establish the height, figure out the height, multiply by the width, and add these things up. This is a complex way to write that. All right, so let me show you an example using a table. I like to use a table to try to figure out how this works because it kind of connects to what's going on here. We have some sort of a function, I don't know what it is, x squared plus 4x, some sort of shape. We want to start at x is 0, we want to end at x is 4, and we're going to use the right side of the rectangles with n equals 4, meaning we're going to divide into 4 rectangles to approximate the area of the region. Okay, so to do that, we're going to divide this into 4 rectangles. We're going to divide them equally. So that means that we're going to have these little intervals here. Right, so what we're going to do is make a table, and at the top of the first column I'm going to put interval, and I'm going to list the 4 intervals that these rectangles are going at. So we're going to have one rectangle that goes from 0 to 1, since I'm dividing this distance from 0 to 4 into 4 equal spots. This is going to go from 0 to 1, and I'm going to have something that handles the distance from 1 to 2, from 2 to 3, and from 3 to 4. And we'll end up summing up little rectangles here. Okay, to use the right-hand side, that means for this first rectangle, we're going to have to pick the value for x. We're going to choose the right-hand side. Right? So that means that we will use 1, the value on the right here for that. When we find the area, we're going to have the height. So the height of this rectangle is going to be f at that value. Right, so to find that, we're going to plug this x value of 1 into the function, and that's going to give me 1 squared plus 4 times 1, which is 5. So 4 plus 1 is 5. That's the height of this rectangle right here, 5. And then we're going to take that height and multiply by a width, which is a little change in x. Right? So how wide is that width? Well, the interval goes from 0 to 1, so this width is 1. And if I take 5 times 1, that will give me the area of that one rectangle. It's 5. That means there are 5 units of area inside that one rectangle. And then we're just going to repeat that for each of the other rectangles. So when I move to the next one, we're going to use the right value for that x, which is 2. We're going to plug that into the function to get the height. So that is 2 squared plus 4 times 2, so that is 4 plus 8 is 12, times a width, which is also 1, equals an area of 12 in this rectangle. Now, this is not to scale, but we're just finding these individual areas. Right, we use the right x value here, plug that in, 3 squared plus 4 times 3 turns out to be 21. 21 times 1 gives me an area of 21, and the last one, we're starting at x is 4. 4 squared plus 4 times 4 turns out to be a height of 32, and 32 times the width of 1 is 32. And then we can sum these values together. If I add the 4 rectangle area up, I end up getting 70. So you can write this operation out in a table. I think that's a great way to do it. Then we should probably say this, the area. I'm just going to write it a little bit different way. It's this width, this height 5 times the width of 1, plus this height of 12 times the width of 1, plus this height of 21 times the width of 1, plus this height of 32 times the width of 1, and that all adds up to 70. Somehow in your work, whether you write it in a table or this way, you have to indicate that you're doing a summation of these things. So if you want to do it more compactly, you can do it this way. But I kind of like this structure because it connects to what's going on geometrically in the sum. Okay, so this is an approximation for the area. Is it going to be exactly right? Probably not. I'm thinking that this is an increasing function, so probably more realistically, the function looks like this. And if we keep using the right-hand side for these things, this is going to be overestimating the area because there's going to be some extra area included. So this is probably too high, but this is one way to find an approximation for the area. Okay, now of course this approximation would be more accurate if we included more rectangles. So what we could do is say, what if we allow the number of rectangles to approach infinity? Well, then rectangles would be super, super narrow, but they would be filling in almost the perfect shape, and you would get essentially the area itself. If I take that same structure and I just took the limit as it approaches infinity, that would give me the actual area. That is defined as the actual area because it's perfectly fitting the curve shape. So the fundamental theorem of calculus, which we're going to learn about in a later section, is going to show that this limit is actually related to our antiderivative. That's the definite integral. So we actually reuse the same symbol. Let me show you what I mean by that. Right? This width right here, this b minus a over n, it's a little change in the x direction. Right? So we just replace that with the differential dx. Some tiny change in the x direction. The f of x height, we just make that the integrand of an integral. And then this summation of an infinite number of rectangles that gives a smooth summation, that is replaced with our integral symbol. That's actually why it looks like this, because it looks like an S that's been elongated, and it does stand for summation, just like this stands for summation, except that we put the value for x at the bottom and the value for x at the top. So if we're integrating from, like that last example was, we're going from 0 to 4, that means we would say that this is an integral from 0 to 4 of f of x dx. Now we already have this symbol, and we know that that represents what we call the antiderivative. Right? Or we call this symbol with numbers here the definite integral. Okay, and we'll see how it connects to that later. But for now, just trust us that we use the same symbol, we put numbers here. If we have numbers here, it's supposed to represent the area between this function curve and the x-axis. Right, so now the examples we've seen so far, f of x has always been positive, right? So we can have rectangles here that are adding positive area. What if we have areas like this where we have negative area? Well, you can handle it a couple different ways. The default way is to just go ahead and let the negative area cancel out part of the positive area. So you could get a total area that's 0, an area that's negative overall, or an area that's positive. If for some reason we want the physical area, we have to be cognizant of the fact that the heights are negative in some region. Take this part and find that area separately and negate it, so we can then add it to the positive area to get the total area. And in general, we do want the negative to cancel the positive, and we'll see that more when we do applications later. Okay, so now we're going to define something formal called a Riemann sum. When we use shapes to compute an area for a curve that we're finding approximately by filling that shape with an infinite number of these things, or a finite number of these things, we call that a Riemann sum, named after a mathematician. The formal definition is this: let f be defined on the closed interval from a to b, and let delta be a partition of a and b such that you divide that into a series of different x's that all go from a to b in order, where delta xi is the width of the ith subinterval. If Ci is any point in the x subinterval, so a selected x, then the sum from I equals 1 to n finite rectangles of the height f of c times the delta x for that width is called a Riemann sum of f for the partition delta. So a few things to note. First of all, the function curve, nothing in here about being positive or negative. So by default, we just go ahead and allow these to be positive or negative, and that means negative area cancels positive. The shapes actually don't have to be the same width. There's no reason this has to be the same width, although we often make them the same width. And in fact, the shapes don't technically have to be rectangles, although I think we call it Riemann sum. This structure does indicate that you have a height times a width. So you have to have rectangles to be called a Riemann sum, but frequently they use the same techniques to calculate even though the shapes are not rectangles. So we don't necessarily have to be rectangles. Right, so we're going to do an example. This one says the values of some particular function are shown in a table. So instead of giving me the function in the form like this, where we have it as a function, sometimes they just give us certain individual values in a table. So they're saying here, evaluate a Riemann sum using rectangular partitions, left endpoints, and the specific subintervals indicated here. So I'm going to make a table. I really prefer the table method here. So we're going to say the intervals have to go from x is 0 to 0.5. And then we're going to have something from 0.5 to 0.75. And we're going to have something from 0.75 to 1, from 1 to 1.5, from 1.5 to 1.75. Oh wait, they actually gave me a smaller list, thankfully, because that was going to be a lot of work. They actually told me to just use these. So we're going to use those intervals, thankfully a smaller number of intervals. Okay, so we will go from 0 to 0.75, and then from 0.75 to 1.75, and then 1.75 to 2.0. So we're just using 3 rectangles as shown here. All right, so then we have to select an x in each of the intervals, and they told me to use the left end, so I'm going to use 0 for this first one, 0.75 for the second one, and 1.75 for the third one. Right. And then we're going to plug those values in to find the height, which is f at xi in this case. So if I plug 0 in, I'm just going to use the table. It tells me the height there is 4.32. And if I plug 0.75 in, it tells me the height is 5.79. And if I plug, 2 in, I'm sorry, not 1.75, yes, 1.75. If I plug that in, I get the height of 8.08. So I can get the heights from the table for the selected x's, and then I'm just going to multiply those times the width. And that has to be the width of the interval. So this first interval goes from 0 to 0.75, so that means we're multiplying by 0.75, which gets me an area in this first rectangle of, and we multiply that all out, and it ends up being 3.24. Okay, and then in the second one, the width from 0.75 to 1.75 is 1, so that area is 5.79. Then this width is from 1.75 to 2 is 0.25. So when you take a fourth of that, you get 2.02. That means that the valuation here, the area, is approximately equal to this summation, 3.24 plus 5.79 plus 2.02, which is 11.05. Right, so this is the same thing we just did. Now we're formally calling it a Riemann sum, and I wanted to include this to show you that the width of the intervals does not have to be same. Right? So make sure that you individually calculate the width of each interval. Okay, there's another rule too that is occasionally found on the AP test called the trapezoidal rule. And that says instead of filling this with a rectangle, which is always going to have some parts sticking out on either side, you can fit it better by inserting a trapezoid. So we're going to have this trapezoid kind of laid down on its side, like rotated and laid down here, so that this base here can fit more closely the curve here. And that means that this base 1 here and base 2 are going to be the heights at the two sides. So the area of a trapezoid is 1/2 base 1 plus base 2 times the height. Right, there's the perpendicular height, and then you can think of it as it's like the area of a rectangle, but where this dimension is the average of the two bases. So you add them together and divide by 2. So it's the average height or average width times the height, except on its side, the average of the height on the left and the height in the middle times the height here of the trapezoid, which is really the width. So to use a trapezoid area, we turn it on its side. The height of the trapezoid is actually the width, and then the two bases are the F on the left side and the F on the right side. So to use that same table and to use all the partitions in the table, let's take a look at what that would look like if you did trapezoidal rule. So we're going to have, I still like the idea of a table, but it'd be a little bit different here. So we're going to have intervals. One's going to go from 0 to 0.5. One's going to go from 0.5 to 0.75. One's going to go from 0.75 to 1, from 1 to 1.5, from 1.5 to 1.75, and from 1.75 to 2. Okay, now I'm not going to pick an individual x in here because I'm actually going to have to plug in both sides of each interval. So instead, I'm going to say, let's find the f on the left of the interval and the f on the right of the interval. So if I plug in 0, right, at the two ends of this interval, the two heights are 4.32 and 4.58. And then to find the area, I'm going to use just directly a trapezoid. So the area of a trapezoid, in this case, is going to be 1/2 of the height on the left plus the height on the right times the width of the interval, which is delta x. So we'll just calculate it directly. This is going to be 1/2 4.32 times 4.58, not times, added. It's the average of those two, 4.32 plus 4.58. Add them up and divide by 2 to get the average, and then multiply by the width. This width is 0.5. And so that gives me an area of, let's see, 2.225. So a fair amount of writing to fill the rest of this in. I'm going to go ahead and do that. So now for this interval, from here to here, the two heights are 4.58, 5.79, and so the area is 1/2 4.58 plus 5.79 times the width of that interval, which is 0.25. And that ends up being 1.29625. Okay, the next one, we're going to take the heights over this interval. So that's going to be 5.79, 6.14, 1/2, and then the average, 5.79. Plus 6.14, and then the width of that is also 0.25. That one ends up being 1.49125. Next one, between 1 and 1.5, heights are 6.14, 7.64. Area of a trapezoid, 1/2 times the sum of the two bases, times the width of the interval, which in this case is 0.5. And that gives me 3.445. And then the last two. So heights are 7.64, 8.08. Trapezoid area is 1/2 7.64 plus 8.08 times the width of that interval, which is 0.25. Turns out to be 1.965. And the last one, the heights are 8.08, 8.14. 1/2 sum of the two bases on the left and right. And the width of that interval is also 0.25, gives me this area 2.0275, and that means that the area is approximately equal to the sum of that, which is 12.45. And you can see from the sketch here that that's going to much more closely fit that than, say, this coarse 3 rectangle thing that we did over here, which is vastly underestimating the area. So we got 11.05 there. This is much closer to the real value, 12.45. So the trapezoidal rule is it's more complicated to implement, but it produces a more accurate estimate. All right, so let's stop this. Yeah, a little bit further before we cut this off for the first part. Okay, so the Riemann sum allows any region with a negative x to add negative contributions. That turns out to be really useful. For now, we're just going to use a notation that we call the definite integral to represent this Riemann sum if we're using an infinite number of subintervals. So if you were to imagine that you took an infinite number of rectangles and did that, we're going to use the symbol for the smooth sum from some starting to ending value. The rule for the height is going to be f of x, and the delta x is going to be this. So when we use this, we're essentially not doing trapezoidal rule anymore. We're definitely saying it's rectangles, right? So when we use this where we have numbers here, that's called the definite integral, and it means to compute a value for the summation of the area between the function curve and the x-axis between these two x values. The result will produce a number that represents the area. Okay, if we do not have numbers here, we just use the integral symbol f of x dx, we can call that either the antiderivative, like we did in the last video, or we can now call it the indefinite integral. So indefinite integral means the integral symbol without any numbers, and that means to find the antiderivative, including the plus c. So we're supposed to get a function plus the integration constant. So this will not be a number, it will be an expression. Okay? All right, so let's do, to tie those symbols together as one last example, approximate the value of this definite integral using a right Riemann sum with equal size interval widths. Okay, so if I am taking this function curve, which is x squared, and we're going from 1 to 7, we're going to approximate with 3 equal size widths. So I could do this. I know the width is b minus a over the number of rectangles. So that would be 7 minus 1 over 3 rectangles would be 6 over 3, which means that we're going to divide this into widths that are 2 each. This is going to go from 1 to 3, from 3 to 5, and from 5 to 7. If we're using a right Riemann sum, we're using the right side of each of those to set the height. This is going to result in an overestimation of this curve. Okay, but now we'll just do the procedure. We're going to find intervals. The intervals are going to be from 1 to 3, from 3 to 5, and the rest of the way from 5 to 7. We will select an x value using the right side, so that will be 3 for this one, 5 for that one, 7 for this one. For the height, we'll plug those into the function. The function is this x squared. So that means 3 squared is 9, 5 squared is 25, 7 squared is 49. The width is the change in x, so the widths of each of these intervals is 2. And then we could multiply the height times the area to find the rectangular area. This is height times the width gives me the area. 9 times 2 is 18, 25 times 2 is 50, and 49 times 2 is 98. And when we add those up, we can now say this. The integral from 1 to 7 of x squared dx, which is supposed to represent the exact area of the curve, is approximately equal to this sum, 18 plus 50 plus 98, which is 166. So we're just using this as a notation for the result of a Riemann sum, and it's an approximate result because this doesn't perfectly match the area. Okay, that's where we're going to cut off part 1 video. We'll do something different in the second part.